Can you hear my voice? Yeah, good. Okay, thank you. So, welcome again to the next session of the IVC astronomy workshop. So, today, after 1 day break yesterday, I hope you are doing well and ready to have a lot of new knowledge. And today we will have two lectures. The first one will focus on the magnetohydrodynamics simulation, and it will be two sessions. And in the afternoon, there will be a lecture concerning the simulation of gravitational wave. So for the first lecture will be delivered by Dr. Johan. He is already in Zoom. So time is yours, Dr. Johan, please.
Hello, can you hear my voice? Hello, Pak Ibnu.
We can hear you.
Okay, thank you very much. Okay, so thank you very much for Pak Ibnu for introducing me, and it's an honor for me to give a lecture today in this wonderful event. And I would like also express my sincere gratitude to all the committees and also ITB, especially for Pak Iqbal, who invited me to giving a lecture today. And as you know that today we will study about the solar magnetohydrodynamic simulation. So I hope you will stay focused and enjoy this lecture. Can I share my screen? Yeah, unfortunately, the host disabled me to share the screen. Oh, okay. Okay, can you see my screen now? Okay, so I hope you... Okay, thank you very much. Okay, so today I'd like to give a brief introduction about the solar magnetohydrodynamics simulation. And this is, yeah, maybe, I don't know, maybe some of you already know about hydrodynamics, or maybe about Maxwell equations, and maybe some of you also already familiar with simulation. But I'm not sure that maybe not all of you maybe already know about the solar physics. So in this lecture, I will introduce first about at least very brief introduction about solar physics, and then I will talk about the definition of the magnetohydrodynamics, and then I will show you some simulation of solar magnetohydrodynamics. And as you can see, for you that who are unfamiliar with magnetohydrodynamics, then maybe you would think that what kind of stuff is this? Yeah. So because the name is very strange, and I will see it later that yeah, maybe this 2 sessions lecture is too short to know about everything about solar magnetohydrodynamics. But at least I hope you will get some feeling about what magnetohydrodynamics is and how we can use this science to understand about the solar physics, and maybe you can apply this science also to other studies that you are interested in. So I'm Johan Muhammad. I'm from Research Center for Space, National Research and Innovation Agency, BRIN or BRIN. So today lecture I will have two parts. The first part, in the first session, I will first introduce about the solar physics, a very brief introduction about solar physics to cover maybe some of you who don't know anything about solar physics. And then I will explain about what is magnetohydrodynamics, and then MHD framework, and then MHD equations, and then some concepts and parameters in MHD. And then I will explain about magnetic reconnection, MHD waves, and I'll give you a summary of this first session. And then we are going to go to the second part after the break, I think. So let me start first with the introductions about solar physics. Yeah, so before I move to the solar physics, so actually this is a quite tough subjects, because we have to understand about solar physics, and then we have to understand about the fluid dynamics, and then we have to understand about electromagnetism, and then we have to understand about simulation. So for you who have problem with fluid dynamics and have a problem with electromagnetism, so I guarantee that you will also have a problem with magnetohydrodynamics. But of course, here I will try to explain my best to explain this easily, so you can follow. At least you can know the very basic concepts and the basic equations that we can use for making the solar MHD simulation. So the first part is about the solar physics itself. So why do we study the sun? Of course, sun is the nearest star from our planet, from Earth, and this is very important because if you study about other stars, or maybe about galaxy and other things like that, yeah, those are very far, but sun is the nearest star, so you can, at least you can see or you can observe this star clearer than other stars, and that is very important for you who are interested in stellar physics, that you can see your subjects in more detail by observing the sun, because we have many observatories in ground-based and also space-based that can even go farther very close to the sun. And the sun is also the center of our solar system, so it's very important. So it determines the gravity of other planets and also our planets, and of course the largest mass in the solar system, and of course also the main energy source in our solar system, and also the main driver of space weather. So for you who maybe you don't know the comparison between the size of the Earth and the Sun, and the Sun is very, very small compared to the Earth is very, very small compared to the Sun. So you can see here, you barely see this very tiny Earth here. If we bring the Earth close to the Sun, then it will be very, very small compared to the Sun. If even it's much, much smaller than the prominence. The solar surface temperature is about 6,000 degrees Celsius or 6,000 Kelvin, maybe about 5,700 Celsius or something. And then the mass is very huge, 333,000 Earth mass, and the volume also about 1 million times greater than the volume of the Earth. And the Sun to Earth distance about 1 AU. So I believe you already know about this. And then, as other objects in astronomy, we can see everything. We can see everything with different wavelength, and we can see different feature. And it also happened with the sun. If we observe the sun with different wavelength, we can see same event come with different feature. Here in 1600 angstrom, or it's close to H alpha wavelength, we can see the chromosphere of the sun, and 304 angstrom, 171, 335, 94 angstrom, and 31 angstroms. We see different features of the same event, and because this is the same object, but we see the different layer of the sun. This is maybe in the lower part of the chromosphere, and this is in the corona and the other parts of the solar atmosphere. We have many observatories, ground-based and also space-based telescope, and we can see the sun quite detailed now because we have a very high resolution of solar telescopes, and we can observe the sun in almost 24 hours a day from the space-based observatories. And yeah, you can see that if we observe the sun with different wavelength, then we can see a different feature of the sun or different layers of the sun. So just brief introduction about the solar structures and solar activities. The green ones here are the structure of the sun. First, we have the solar interior, the center of the sun. We have the core of the sun, solar core, which is very, very hot here, where the fusion reaction happen inside of the solar core. And then we have radiative zone and the convection zone, and then we come to the solar surface, which is the photosphere, the surface of the sun, which has the temperature around 4200 to 1600 degrees Celsius. And then we have also the inner atmosphere of the sun, which we call as chromosphere, and the temperature is about 20,000 Kelvin. Sorry, we don't use degree here. And then the corona, the outermost structure of the solar atmosphere, that has temperature up to 2 million Kelvin. And this is very strange because the outer part of the sun, the outer part of the solar atmosphere, which is the corona, has higher temperature than the inner part. And it's still the issue for many scientists to understand why there's a coronal heating. What kind of mechanism that make the corona become much, much hotter than the photosphere and the chromosphere. And I still don't know exactly what is the answer. So here, the yellow box here show some of the activities that happen in the sun. First, we have the prominence or the solar filament. Here, we can see the filament or prominence is the bright feature extending outward from the sun's surface into the sun's atmosphere. Well, actually, this is high plasma density but low temperature that is lifted up to the atmosphere of the sun, so we can see this bright feature like this. And then the coronal hole, which is the area in the corona that appeared dark in X-ray and ultraviolet image of the sun, darker from its surrounding. Usually we can see the coronal hole in the sun's poles, north and the south, and also sometimes it appeared in the low latitude like this. And then we have sunspot. Maybe you all already know about this. The sunspot is the black spot on the surface of the sun that has lower temperature than its surrounding. And I will show you in detail what are these activities in the next slide. And then we have the solar flare, which is a sudden increase of electromagnetic radiation and high energy particles from a region in the sun due to the release of energy to the interplanetary space. So these are the solar structures and also solar activities. And then we will we'll look in the more detail in the next slide. First, we have to know about the active region. What is active region? So active region, if you see the sun like this, then you may see that in some part of the sun, there are several regions that are brighter than others. This part we call active regions. If we zoom in this region, then we can see bright features like this. This is solar corona. If we observe from the wavelength of 304 angstrom, but if we see the sun from different wavelength, if we see this region in different wavelength, you can see that actually in the photosphere, then this bright feature are associated with this sunspot. The location is almost the same. So basically, if we observe this sunspot in the atmosphere, then we can see the bright features like this. This is what we call as active region. So active region is a region in the sun that has strong concentration of magnetic field, where sunspots and flares frequently happen. So because it has strong concentration of magnetic field, here is the observation of the sun, of the solar surface from magnetogram data that we can see the magnetic field strength of the surface of the sun. Then we can see that right in the region where sunspot appear, we can see that there's strong concentration of magnetic field. The white region represents the positive polarity region, and then the black region shows the negative polarity region. So we can see there's a couple of magnetic field like this. And if we can draw some field line, if, for example, this is the surface of the sun, then we can see the sunspot like this. So there must be a field line connecting this sunspot pair like this. So magnetic loops are anchored in the sunspot pair like this. So we can imagine that there's a magnetic field line around here and also the magnetic field line around here. And that makes the sunspot look like this. And also sometimes we can see these magnetic field lines in the corona here. So that is the active region. It's important to understand that the sunspot and flares, usually they occur in active region. So what is solar flare? The solar flare happens because of the release of magnetic energy that is transformed to the electromagnetic, thermal, and kinetic energies to the solar system. So I already mentioned about the solar flare in the previous slide, that the solar flare is the sudden increase of electromagnetic radiation. This is observation from GOES satellites. We observe the sun in different wavelength, and then we can see that this is on December 13, 2006, when the X 3.4 flare happened. And then we can see right in after the beginning of the December 13, then there's a sudden increase in the X-ray radiation that was received by the GOES satellite. If we observe that flare from this active region, we can see that suddenly there's some kind of a flare ribbon like this in the sun. We know that there's a flare happened by observing the GOES X-ray flux and also by observing the sun directly with this one with the HINODE SOT telescope. So people then try to model the flare, and this is the standard flare model, which people believe happen when the flare occur in the sun. So actually, there's a magnetic loop like this, but then suddenly something happened that makes magnetic reconnection to occur. We will later study about what is the meaning of the magnetic reconnection. And then due to this magnetic reconnection, then some of the energy are transformed to the other forms of energy like electromagnetic and also thermal and kinetic energies. And then there's also coronal mass ejection, or CME, and flares are often accompanied by CMEs when prominence or filaments are erupted and unleashed huge amount of high energetic particles to the interplanetary system. So this is the sun observed by the Soho-Lascaux coronagraph. It's just mimicking the solar eclipse, so we can see the corona for 24 hours. So if we see the sun when CME happened, then we can see there's some kind of a eruption of the coronal mass like this. And this coronal mass ejection can reach Earth within 2 or 3 days. And fortunately, that the Earth's magnetosphere can become a very powerful shield that protect us from this massive particle bombardments. So CME speed is very, very fast. You can imagine that we have very, very huge explosion like this with the speed of 600 up to 3,000 kilometers per second. This is not kilometer per hour, but kilometer per second. So it's very, very fast. It could be very dangerous for our Earth if we don't have any protector like this. And then I will also explain about the solar cycles. So if you observe the sun in solar minimum phase, maybe you will not be able to see any sunspot like this. It's very clean. But in another time, maybe several years later, then you can see that the sun full of sunspot like this. So sunspot occurrences are varied in time, so it's not always the same. So sunspot occurrences in the sun have a cycle, which has approximately 11 years period for one cycle. And people already observed this variation of sunspot for many centuries, at least few centuries. So 3 or 4 centuries back, people observe the sun and they see there's a cycle of a sunspot like this. But the amplitude of the solar cycles is different from time to time. And then by analyzing the signal of this solar cycles, then scientists try to predict the next cycle. This red lines show the prediction for this solar cycle today, which is a solar cycle 25. And as you can see, this blue dot lines show the real observations of the sunspot number, then people know that, yeah, this is not very good prediction. You can see there's a discrepancy between the observations and the prediction. So even if we know sunspot and we already observe sunspots for many long times, but we still cannot understand the real mechanism that generates sunspot. So we still cannot predict the next solar cycle accurately. And then, well, let's come to the more physics of the sun. We know that the sun is full of plasma. So because the sun is very hot, so the materials there become plasma. What is plasma? So if we know that if we have a material, then we can get several types of phase of materials. First, we have a solid phase, which is the strongest. The bond is very strong between the molecules or the atoms. And then if we give more temperatures and energies to the solid phase, then it will turn to the liquid. The material will turn to the liquid, which has more, how to say, loose bond or interaction between the molecules and the particles there. But if we give more energies and temperatures, then this liquid material will become a gas. And this bond between each molecule is very much weak, and each molecule can freely go whatever they want. But what happens if we give more energies and temperatures to this gas? Then the molecules here and the atoms here can become ionized. So we call this as plasma. Many people think that plasma is the fourth state of matter. So plasma is the ionized gas with mixing ions and electrons. We can say that plasma is roughly neutral or quasi-neutral, because the number of the ions and the electrons almost the same. And sometimes we also have the neutral particles there. And so we can imagine that the sun full of plasma like this. So the sun is not solid, it's not liquid, it's not gas, so it's plasma, so ionized gas. And then not only the plasma, but also sun is a very highly magnetized environment, because in almost all the sun's surface and also sun's solar atmosphere, there's a magnetic field, and the dynamics of magnetic fields in the sun play very important roles in the occurrences of many solar activities, as we will see later. If we can extrapolate the magnetic field in the sun, then we can see that the sun is full of magnetic field lines connecting each other, and then it's very complicated like this. If we focus on just in small part of the sun, we can see that we can really observe the magnetic field lines like this. Well, actually, we cannot observe magnetic field line, but we can see the proxy of the magnetic field lines by the emitting plasma that emits radiation from it. So we can see something like magnetic loops like this. So suppose we have sunspot here. So we can imagine that just beneath the sunspot we have positive polarity and negative polarity of magnet like this. So it's very important to understand that the sun consists of plasma and also magnetic fields. So That understanding is very important because we want to know about magnetohydrodynamics, and everything about magnetohydrodynamics is related with plasma motions and also the magnetic fields. So we already know about plasma. It's the ionized gas, and we also know that there are so many magnetic field lines in the sun, and this plasma and magnetic field, of course, they are interacting with each other, and then if we study this plasma motions and also the magnetic fields of the sun as a macroscopical motions, we can consider that the plasma motions macroscopically as a conductive fluid motion. So we can imagine that plasma is just like a fluid, but very conductive. And because it's a conductive fluid, if we have magnetic field, then of course it will interact with the magnetic field. So the mutual interaction of a conductive fluid and a magnetic field is the subject of the MHD study. So MHD studies about the plasma interaction with magnetic field and the mutual interaction between these two constituents. So we must know about fluid dynamics and the magnetic fields. And then if we combine this science or this knowledge, then we can get the magnetohydrodynamics. Okay, so before we go into the detail about the MHD, we have to know about the MHD framework, because not every features in the sun we can study by using MHD approach. So there's some limitation of the MHD framework that you should know, that if you want to do like MHD simulation, then solar activities that you can study by using MHD, or do you need to use another science, which may be some kinetic theories and others. So the first thing that we should know is the Debye shielding. So what is Debye shielding? For example, we have a large collection of charged particles here. This is the ionized gas, and then we put some test charge in the center or somewhere inside of this charged particles collection, and then of course there will be interaction between these particles. Maybe we have positive charge and negative charge. Then we know that there's a electric potential, so we have Coulomb's law that some of magnetic charge will be interacted with the opposite charged particles. But if we have so many particles like this, then there's a limit where the effect or the influence of this test charge will be effective. Whether while outside this volume, then we can say that the electric potential of this test charge is not very effective. So that is the definition of the Debye sphere. And the radius of this Debye sphere, as we call it, as the Debye length. So why Debye sphere and Debye length is very important, because in order to use the magnetohydrodynamics, we have to make sure that the plasma is neutral, because the ionized gas is not always neutral. Sometimes if there's only very few ionization, then most of the gas maybe are still not ionized and it's still not in neutral condition. So we have to make sure that that this large collection of charged particles is neutral plasma. So how we can know that is when they are electrically neutral to a high degree approximation. So the positive number of the number of the positive particles is almost equal to the negative particles. So the dBi length is the distance over which the electric field of a test charge in the plasma is screened by the plasma. And we can calculate dBi length here as like this. So we need the permittivity and then Boltzmann constant and the temperature of the plasma over the number of the particles and also the charged particles square like this. And then we can see that inside this dBi sphere, or when the radius of the dBi or the radius of our interest is still smaller than the dBi length, then the Coulomb potential is still effective. But outside the sphere, then very far from the sphere, and then the Coulomb potential is very much small. And we can consider which plasma is neutral or not by examine our scale length of the object that we are studying. If the scale length of the object is much greater than the dBi length, then we can consider that that plasma is neutral. And we can know that the number of particles in the dBi sphere is very large because it's proportional to the cubic of the dBi length or the radius of the dBi sphere. Here are some examples of the dBi length and plasma density for many medium, for example, ionosphere, magnetosphere, solar core, solar corona, solar wind, interstellar medium, and even intergalactic medium. For the solar corona, because we are interested in solar corona here, so you can see that the dBi length is very small. So it's only in the order of 1 centimeter approximately. So if we study about solar corona, then it's already, the scale length is much greater than 1 centimeter because, you know, the corona is very big. You can see that in the first image I showed you, the size of the prominence is very large, even bigger than the Earth. But in the very high medium, like interstellar or even intergalactic, you can see the dBi length is also very large. So you can guess that the number of particles in dBi sphere in the intergalactic medium is very large. And another thing is the Larmor radius. So we know that in the presence of magnetic field, a moving charged particle will experience Lorentz force. This is very simple equations. You know about this from high school. If we have a charged particles, then it moving around the magnetic field, it will get the force, the Lorentz force like this, where Q, V, and B represent charge, velocity, and magnetic field respectively. And this force can cause an electron or ion spiral around magnetic field lines, creating a helical trajectory. And the radius of the helical orbit is known as the Larmor radius, or RL here. So if we have magnetic field lines like this, and then we have ion moving in perpendicular direction, then it will experience the Lorentz force, and it will make a spiral trajectory like this, and also for electron orbit. And the radius of this gyration motion, we call it as a Larmor radius. So if we imagine that there's maybe this image is not very good. If we have ion moving in a magnetic field like this. So we have a gyration motion of the ion and also the electron. But if we consider this as a unity, it's a very large collection of ion and electron moving, spiraling the magnetic field lines around there, then we can think this as a very large fluid, conductive fluid motion. So MHD does not treat each individual particle, but consider the plasma as collective particles and magnetic fields. So it's important to understand that in MHD, we think that plasma and magnetic fields as a unity, and we don't treat each individual particles and interaction between them, but consider ions, electrons, and all these constituents of the plasma moving together with magnetic field, and that is the MHD framework. MHD framework regards plasma as continuous medium, that the length scale is larger than the Larmor radius. So it's very important. First one to understand that the dBi length, or the length scale of our interested subject is much larger than the dBi length, and the second one is the length scale is larger than the Larmor radius. Then we can use the MHD or MHD framework for our study. Okay, so now we are going to go to the more details about the MHD equations. So as I already mentioned earlier, that we are talking about magnetohydrodynamics, then we are talking about the fluid dynamics or hydrodynamics, and also the electromagnetism. So the first one, we review on hydrodynamics, the basic equation of hydrodynamics. We have the continuity equations or the mass conservations. Mass coming in equals the mass coming out. And then we also have the momentum equation or the equation of motion like this. I believe you already, maybe at least you already see this kind of equations in your, maybe in your previous lectures, maybe. And suppose that we also have the energy equation like this. This is just a simple adiabatic equation. So maybe we don't discuss about this very much, where d over dt is equals to the dou over dou t plus v dot divergence dot nabla, the total time derivative in a frame of reference moving with an element of plasma. Okay, so we know the hydrodynamics equations is basically only like this. And then we also already learned about the Maxwell's equation, or the law that govern all the electromagnetisms. The first one, we have the Gauss law for electricity, that the divergence V equals to the electric charge density over the permittivity, electric permittivity. So I hope you already understand about this. So I will not explain in detail about this, but actually this one explain about that if we have a charged particle, then the electric field will come from that charged particle to all direction, and the amount of the electric field will be proportional to the amount of charged particles. And then we have also the Faraday's law, that the cross E equals to minus dou V over dou T. And we will see later about this one, because this is very important. Well, actually, this one is, we will not use this in the first equation. Divergence E equals rho over epsilon. We will not use this in a plasma, because plasma is quasi-neutral, or we can say plasma is just neutral. So we don't have a charged particle in macroscopically. We don't have imbalance problem there. So we will omit this first equation, or Gauss law for electricity. And the third one is the Gauss law for magnetism, that the divergence B equals 0. So it means that there's no like monopole magnet. So okay, we assume that there's no monopole magnet here. And then the last one is the Ampere's law, that the cross B equals to mu J plus dou E over dou T over C square, speed of light. So this one, maybe we will not use this because this one is very small, so we can neglect this. But this one is very important. It shows that if we have a wire with electric current, that we have a surrounding magnetic field, something like that. So we know that is the Ampere's law. Okay, so by using this hydrodynamics equations and considering this Maxwell equations, then we can come to the MHD equations. As you know that the plasma is the conductive fluid, and if it moves, or the plasma motions can be approached by the hydrodynamics, and because there's a magnetic field, a very strong magnetic field, and it follows the Maxwell equation, so we need both the hydrodynamics and the Maxwell equations. Then we come to the basic MHD equations. Let's now see the first equations, the continuity equation. There's no problem with this. And then, but the second one here, we know that the actually this one, the left-hand side, this is this force. So we know that the force can come from the gradient of pressure, which is the plasma pressure here. And then the force can also come from gravity, but we can omit this for several reasons. We usually don't use this in magnet hydrodynamics, at least for the zero beta. Then we can learn about this later. But then there's a new term here, appeared here, which is the Lorentz force, which come from the interaction between the plasma and the magnetic field, plasma motion and the magnetic field. So we have a current and we have a magnetic field, then there will be a Lorentz force. So this is the addition term that we add to the hydrodynamics equations in the part of the equation of motion. We have Lorentz force here. And then we have also energy equations. So now let's assume we just use something like this, very simple. And then here is the, okay, let me written here. So we have the electromagnetic field here, electric field here, and this E consists of two parts, which is the first one is the ohmic equation, ohmic term. We have the resistivity, electric resistivity, and then we have the current density J. And then we have this is, we already see this in the first part or in the previous slide. I already showed this, that if we have particle moving around magnetic field, then we have something like Lorentz force, something like this, V cross P. So basically the electric field consists of two parts, J part and the V cross V part. This is what we call as the Ohm's law. Maybe you know in high school or in the junior high school, if we should study about the electric I don't know the name, is electric. So you have a wire, and then you have electric current, then you have electric potential there, and then it equals to the current times the resistivity. So it's this, that is the first one here, but the second one is the additional one because of the plasma that we have. We call this the Ohm's law. And the final part is this one, the Faraday's law. So in the Faraday's law, we know that dou B over dou T equals to minus curl E. Okay, and then we have it equals to, because we have E, if we substitute E with this one, we just put it here and we solve this, and then we get this part. So you can try by yourself to expand this equation to get this one. But in the end, we will have the curl of V cross B, and then plus the eta square nabla B. So this is the first term, we call it as the advective term, and the second term we call it as a diffusive term. And this part, we know this as the induction equation. So this is very important equation that we will use mainly in the MHD, which is the induction equation. So we have an advective term and a diffusive term that determine how the magnetic field change in time. And then we have two constraints here. The first one is that the curl B is equal to mu J, and then we can omit this one as I explained before. And the second part is the solenoidal condition that the divergence B is 0. All of these are derived from the hydrodynamics and Maxwell's equations. Okay, then we must understand some useful concepts and parameters in MHD. The first one is the plasma beta. So we recall the equation of motion, the rho dou V over dou T equals to minus gradient P plus J cross B. And we have one constraint about the curl B equals to mu J, right? If we substitute or we substitute this J with this definition, then this Lorentz force will be like this, curl B cross B over mu. It equals to something like this. Then by using some vector identity, you can get this result. First one is the first term here in the left, and the second term here in the right. We call the first term here as the magnetic pressure term, and then the second part is the magnetic tension force or magnetic tension. So this, the first term, acting from high magnetic pressure to low magnetic pressure, this is just almost the same as the plasma pressure, but this is for magnetic field. But second one is the magnetic tension. So magnetic tension is a force that always acts towards the center of curvature. So if we have a magnetic field lines like this, that bend like this, so this magnetic field lines will try to return to the straight again, to straight condition again. What makes that to become straight is the magnetic tension force. So this part try to make the bending magnetic field to become straight, and this one is almost the same like the magnetic or plasma pressure here, but for the magnetic field. So plasma beta is the ratio between the plasma pressure gradient and the magnetic pressure. So this plasma pressure gradient, this one, the P, and the magnetic pressure with this one. So we are not talking about the magnetic tension here in plasma beta. So plasma beta equals to plasma pressure to magnetic pressure. So the same, because this is the same form like this. You can compare this, it's almost the same. So plasma beta value can give important information which part of pressure is more dominant in the system, whether it is the plasma is more dominant or the magnetic field is more dominant, because the sun or our study or our subject is so our interest medium consists of two parts, plasma and the magnetic field, but which one is more dominant? So plasma beta determines that. If we have a very big plasma beta, then plasma is more dominant. If we have a very small plasma beta, then magnetic field is more dominant. And the next parameter is the magnetic Reynolds number. Okay. Sorry. Okay, so this one is a magnetic Reynolds number. So we will recall the induction equation like this. Dou P over dou T equals to curl V cross B plus eta and this part, this one, second term like this. We know that this is this diffusive term and this is the advective term. And if you know that the nabla by definition is something like this. So it's proportional to the length of subject or the length scale. So if we try to see the general value of anything, we just need, or dimensionless quantity, we just need to use the approximation like this. So if a plasma moves with typical speed v and typical length l, then the advective term, the first term here, will become curl v cross b. It will be proportional to the v. This one v b over l, because you know that this nabla actually is just 1 over the scaling. And then the diffusive term will be the eta, and then we have b, and then because this is square, the nabla square, then we have l square, like something like this. This blue one is the diffusive term, and the red one is the advective term. So diffusive term means that there's a diffusion. So you know that the plasma and magnetic fields, that they can diffuse and change to other forms, or they can mix or unite each other. But affective term means that there's some kind of a rotation and turbulence there. So this ratio between the affective term and the diffusion term is called as the magnetic Reynolds number. We call Rm like this, so Vb over L by eta b over L squared. Or you can write like this, and we can get that the magnetic Reynolds number is VL over eta. Eta is the magnetic diffusivity. If we have a very large magnetic Reynolds number, and it's the case in the most astrophysical plasma, then it means that the advective term is more dominant than the diffusion term. Or even we can say that there's almost no diffusion at all. For example, in the intergalactic medium or interstellar medium, we have very, very large magnetic Reynolds number. So the plasma is, the magnetic fields almost, they move together and there's no diffusion at all. But in the industrial plasma, usually the diffusion is quite large, so the magnetic Reynolds number can be smaller than 1. So in the ideal condition, when there is no ohmic dissipation or no diffusion at all, where magnetic Reynolds number is very, very large, then the induction equation becomes something like this. That we don't have the diffusion term. In this case, the magnetic flux conservation will happen, and then magnetic flux in a co-moving surface is conserved. So what does it mean? So if we have a magnetic flux like this, of course, it's also, we have a plasma here. You have two elements of plasma connecting in this field line to this part. We have 1 and 2 here. This is in the same field line here. After several minutes or several seconds or several days or even years or a very, very long time, if there is no dissipation at all or there's no diffusion at all, then even if the shape is changing, then but still these two elements of plasma is still connected. They are still connected to the same magnetic field line. So that's the meaning of the frozen in magnetic flux. It will happen in the system where the magnetic Reynolds number is very, very large. But what happened in the very small magnetic Reynolds number system? If this magnetic Reynolds number is quite small, and there's diffusion happen in the magnetic field that moves with the plasma through ohmic dissipation. In the previous example here, I show you that these two elements are connected to the same field lines for a very, very long time, or maybe forever, for good. But because there's a diffusion, then that's not the case anymore, because the diffusion can happen in a small region, sheet or point, where magnetic field dissipates its energy to other forms by magnetic reconnection. So magnetic reconnection occurs when two opposite magnetic field lines get close together by the flowing plasma and break magnetic conservation by dissipating the magnetic energy to a different form, usually to the electric current. So we have the magnetic field lines towards this side and then to the right side, and below we have magnetic field lines towards the left side. And then there's some motion of plasma that make this two magnetic fields with opposite direction close each other, and then they reconnect each other. Like this, we have magnetic field lines to the right and then magnetic field lines to the left in the bottom. And then when these two magnetic field lines with different or opposite direction meet each other, and then there will be reconnection. So this part will be connected to this part, and that part will be connected to that part. So these two elements are not connected to the same field line anymore. Why? Because there's a magnetic reconnection. And this magnetic reconnection allows the diffusion happen, which means that there's ohmic dissipation, means that some energy, the magnetic energy, are formed to other energy. Then usually we will have an electric current here. So the plasma will move now to this side and to this side, to the right side and to the left side. So the plasma initially move from above to the bottom and bottom to up, and then now it will move to the left and to the right. So this is the role of magnetic reconnection. So magnetic reconnection make the diffusion to be realized, and then that is because the small magnetic Reynolds numbers like this, which means that the diffusion term is playing some role there. And then we will move to another topic, which is the MHD waves. So we know that in the hydrodynamics we have sonic or sound wave. And we know that this restoring force is plasma pressure gradient, longitudinal. We know that in hydrodynamics, we don't have a magnetic field there. So only the particles in the air maybe. So we have changing of density here. And then because of different of plasma pressure gradient, then we can hear a voice, and the direction is longitudinal. And we can calculate the speed, the sound speed like this. But in magnetohydrodynamics, we also have plasma and also a magnetic field. So there's another possibility of wave that we can obtain. First one is the Alfvén wave. So Alfvén wave is the wave that the restoring force is the magnetic tension. And the shape of the wave is transverse, the transverse wave. So for example, you have magnetic field lines like this, and because of the motion of plasma or anything, then the shape of the magnetic field lines can be changing, and then but there's a magnetic tension force that try to make this bending magnetic field lines become straight again. Then because of this restoring force, then we will get, or we will have the Alfvén wave that moving parallel to the magnetic field lines, but it's a transverse. So we have some kind of a sinusoidal shape like this. And we can calculate the speed of the Alfvén wave like this by this equation, p squares over mu rho. And also we can have a compressional wave, because if we have the magnetic field lines which has different pressure like this, then we can get almost the same like this sound wave, but this is perpendicular to the magnetic field lines. This is some of the authors consider this also as the compressional Alfvén wave, but some others they don't think this is the same Alfvén wave, so we don't use the Alfvén wave here. Alfvén wave is this part, but some of them they wrote that this one is the shear Alfvén wave and this is the compressional Alfvén wave. Wait, anyway, we have the Alfvén wave that is transverse and also the compressional wave like this. But then we have another MHD waves, which we call as the magnetosonic wave. We know that in the sound wave, we only consider about the plasma pressure here, gradient of plasma pressure. But in the Alfvén wave, we only consider about magnetic tension. So this is all about the magnetic field lines. But if we have the plasma and magnetic field together, then we will get the magnetosonic wave. Here we have two modes. The first one is the slow mode and the fast mode magnetosonic waves. And the restoring force are plasma and magnetic pressure gradient. So the plasma pressure gradient and magnetic pressure gradient, and also the magnetic tension. So we have all of the plasma pressure gradient and magnetic pressure gradient, and also magnetic tension to form the third form of the wave, which is the MHD waves or the magnetosonic waves. And it has dispersion relation like this, which is it's depending on the sound speed and also the Alfvén speed. As you can see here, the red one here represents the equation for the fast mode, and the blue one here, the minus sign here, correspond to the slow mode wave. So if we want to have this dispersion relation of the fast mode magnetosonic wave, we use the plus here, and if we want to know about the slow mode wave, magnetosonic wave, we use this negative sign. And you can see here that in the direction perpendicular to the magnetic field, where perpendicular to the magnetic field means that the theta is 90, or this term will be 0, and then we get the slow mode will vanish, and the fast mode propagates at cs square plus va square. Va is the Alfvén velocity. So this is the simulation of the magnetosonic wave. This one is for the non-magnetized plasma, so we only have the sound wave. So if you have the perturbation here, then the sound wave will propagate to all directions, just like this one. But in the highly magnetized field, then the plasma, if we have a perturbation in the plasma, then the wave will come and then propagate to the direction parallel to the magnetic field, very strong like this, but perpendicular to the magnetic field is quite weak like this one. But in the weakly magnetized plasma, we can see that the shape is almost close to the non-magnetized plasma. It has very strong sound wave, and then the wave that is perpendicular to the the parallel to the magnetic field lines will be a little bit weak. You can see this explanation and also the simulations by Tetsuya Magara in this link. Okay, so now we come to the summary of the part 1. First, that the solar physics study many phenomena that can be observed through ground-based and space-based telescope. For example, sunspot, prominence, solar flares, CMEs, and others. And solar physics is related to the nature of plasma in the highly magnetized environment, because usually the magnetic field in the sun is very strong. And you know that if we have plasma and magnetic field, then we need more different approach for that. And that's why we need the MHD. So MHD is the science that study conductive fluid, which is plasma, in the magnetized environment, which is the sun. And we know that MHD equations are derived from the hydrodynamics and also Maxwell's equation. So we already learned about this this morning, and I hope you get some feelings about what magnetohydrodynamic is, and at least you know the basic concept of the magnetohydrodynamics, which is the definition, and then the framework, and then the equations that we use, which is derived from hydrodynamics, and also the Maxwell equations. So yeah, in the second part, we will study about how then we can use these MHD equations and what kind of solar phenomena that we can study by using MHD approach, and what people are doing out there when they use MHD for making some simulation of solar phenomena. So I think that is the end of my first session. So I will return it to moderator, Pak Ibnu.
Okay.
Do we still have time also?
Yeah, thank you very much for this really clear explanation. So is there any question from students? Be in chat. I will check by myself. Okay. Okay. So if not, I have a question for you, Dr.
Yes.
Johan. Yeah, I just wondering, how does a satellite or spacecraft protect themselves from CME? Because they are not coverage by the magnetosphere of Earth normally, right?
Yes, yes, yes. Yeah, yeah. This is a very interesting problem that uh, many satellites face today because you know that the satellites or spacecraft they are located in the region where there's no protection from the magnetosphere. So yeah, basically they already equipped themselves by some materials which unfortunately I don't know exactly, but yeah, but still they will suffer that kind of uh, disturbance in their system when there's a very strong CME or solar flare happen. Then usually there will be some kinds of anomalies in their system, and we and BRIN here in Research Center of Space also study about the anomalies of many satellites and spacecraft during the space weather disturbance when there's very large flares or very large CMEs happen. But yeah, but not always. So because not every CME always come to Earth. You know that the interplanetary space is very large and the Earth is very small. So the opportunity that CME comes to Earth is not 100%. So some CMEs they go to different direction, and maybe we just get the very edge of the CME, so not very strong. But if the CME is very strong, and then if the direction is very much right, exactly to the spacecraft, then some spacecraft can get lost. Yeah, so that's the problem that we still are trying to figure out how to find a solution for that. But yeah, they of course they already equipped their satellites with some protections, some very specific materials, but still, well, because the SIM is very strong, then it's very difficult to handle that. And also there's also now there are so many solar observers in the space. Some of them they observe the sun in a very extreme condition. So one of them is the Parker Solar Probe in the PSP spacecraft. So PSP spacecraft. So its orbit is very extreme, so it can reach the outer part of the corona, and the temperature could be very high. And what they're looking for the CME. So they try to seek the CME. They will be happy if the spacecraft will be hit by CME, I think. Yeah, of course they already prepare for that, but I don't know how and what kind of materials they use for that protection. But still, yeah, that's one of the big challenge in our generation, how to protect the spacecraft and satellites from such kind of disturbance from CMEs and also solar flares.
Okay, thank you for the answer. So, anybody have a question now? If not, maybe we will have a short break for 15 minutes, maybe, and we will get back at 9:45, right? Yeah. Okay, so see you there.